Welcome to Elementary Real Analysis. Today we are going to explore one of the most foundational concepts in all of mathematics, convergent sequences. If you have ever wondered how we can rigorously talk about infinity or how calculus actually works behind the scenes, you are in the right place. We will build this idea from the ground up, starting with simple intuition and moving to the exact mathematical definitions used by mathematicians worldwide. Let us dive in. Now that we are ready to begin, let us start with a simple thought experiment. Imagine you are walking toward a wall that is exactly 10 feet away. On your first step, you cover half the distance, leaving you 5 feet away. On your next step, you cover half the remaining distance, leaving you 2.5 feet away. If you keep doing this forever, you will never actually bump into the wall, but you will get infinitely close to it. In mathematics, the list of your distances from the start is called a sequence. The wall represents the limit, which is the exact numerical destination that the sequence is trying to reach. When a sequence successfully homes in on a specific target value like this, we call it a convergent sequence. Building on that intuition, we must realize that simply saying numbers get closer and closer is not mathematically strict enough. Sometimes numbers get closer to a target but never actually reach it, like a car slowing down but stopping a mile short of its destination. To make this rigorous, mathematicians use a very strict test involving a Greek letter called epsilon. Think of epsilon as an error tolerance or a tiny target zone drawn around the limit. The formal definition states that a sequence converges if for any strictly positive error tolerance, you can find a specific starting point in the list called the threshold index n. From that threshold point onwards, every single number in the sequence must fall inside the error tolerance zone and stay there forever. Now that we understand the concept of an error tolerance, let us look at the mathematical formula that defines convergence. The formula states that the absolute value of xn minus L must be strictly less than epsilon. Conceptually, this comes from measuring the physical, positive distance between our sequence and our target. Here, xn represents the value of the sequence at position n. L represents the limit, which is the final destination value. The vertical bars represent the absolute value, ensuring we measure a positive distance, regardless of whether the sequence is above or below the target. Finally, epsilon is our chosen error tolerance. If we decrease epsilon, making the target zone smaller, we simply have to go further down the sequence to a larger position n to ensure the distance shrinks enough to satisfy this strict condition. To truly grasp this formula, let us visualize it with a diagram. What you are looking at is a graph where the horizontal axis represents the position index n and the vertical axis represents the sequence value. The central horizontal dashed line is our limit L. Notice the shaded horizontal band stretching from slightly below the limit to slightly above it. This is our error tolerance zone, defined by epsilon. Look at the early points in the sequence on the left. They jump wildly outside this band, representing unpredictable early behavior. However, follow the horizontal axis to the critical threshold index n. Once we pass this vertical line, every single subsequent dot is permanently trapped inside the shaded band. If we chose a smaller epsilon, the band would shrink and we would just have to wait a little longer, finding a new larger n further to the right. Before we move on to more complex ideas, let us see this definition in action with a concrete example. We want to prove that the sequence defined by the formula 1 divided by n converges to the limit 0. We are given the sequence and the target limit, and we are asked to show that for any tiny positive number epsilon, we can find the threshold index where the sequence stays within that error tolerance. We chose this approach because it is the formal requirement for convergence. We start by setting up our absolute value inequality. Next, we substitute our specific sequence, 1 over n, and our proposed limit, 0. Subtracting 0 does not change the value, so we can easily simplify the expression inside the absolute value bars to just 1 over n. Continuing with our simplification, we can now solve for the position index n. Because the position index n is always a positive whole number, the fraction 1 over n is always positive. Therefore, the absolute value bars are no longer necessary and can be safely removed. Our objective is to isolate n, so we know exactly when the sequence crosses into the safe zone. We multiply both sides by n to get it out of the denominator and then divide by the positive number epsilon. This gives us our final inequality. N must be greater than 1 over epsilon. Physically, this means if someone gives us an error tolerance of 0.01, we plug it in to find that n must be greater than 100. We have definitively proven that the sequence converges to 0. Now that we have successfully proven a simple sequence, let us tackle a slightly more complex rational sequence. We want to prove that the sequence defined by 2n plus 1 divided by n plus 3 converges to the limit 2. We are given a fraction that gets very close to 2 as n becomes massive, and we are asked to prove this rigorously using the exact same epsilon method. We start by setting up the absolute value of the difference between our sequence and our proposed limit. To subtract the whole number 2 from our fraction, we must rewrite 2 as a fraction with the same denominator, which is n plus 3. This means we multiply 2 by the fraction n plus 3 over n plus 3, setting the stage to combine everything. Continuing our algebraic manipulation, we now combine the terms inside the absolute value into a single fraction. This is a standard algebraic technique to simplify differences involving fractions. Next, we distribute the negative 2 across the terms inside the parentheses in the numerator, which gives us minus 2n minus 6. Now we can combine the like terms in the numerator. The positive 2n and the negative 2n will perfectly cancel each other out. This cancellation is exactly what we want to happen when proving a limit, as it removes the variable from the numerator and leaves us with a much simpler fraction, negative 5 over n plus 3. With our fraction simplified, we must now deal with the absolute value bars. The absolute value of a fraction is simply the absolute value of its numerator divided by the absolute value of its denominator. The absolute value of negative 5 is simply positive 5. Looking at the denominator, since the position index n is always a positive whole number, the expression n plus 3 is always positive. Because both the top and bottom are now strictly positive, we can completely drop the absolute value bars. We have successfully stripped away the absolute value and simplified the expression to 5 over n plus 3 is less than epsilon. We are now ready for the final step of isolating n. For our final steps, our goal is to isolate the position index n. We can multiply both sides by n plus 3 and divide both sides by epsilon. Then we simply subtract 3 from both sides. This formula gives us our exact instructions for finding the threshold index n. If someone challenges us with an error tolerance of 0.1, we plug it in to get 5 divided by 0.1 minus 3, which equals 47. This guarantees that after the 47th term in the sequence, every single number will be within 0.1 units of the limit 2. Because this formula works for any positive epsilon, we have rigorously proven that the sequence converges to 2. Now that we have worked through these rigorous proofs, you might wonder why mathematicians insist on such a strict, tedious process just to prove something that seems obvious. The reason is that human intuition completely breaks down when dealing with infinity and highly complex functions. Convergent sequences are the absolute bedrock of all advanced mathematics, including calculus. When you calculate a derivative to find the speed of a car or an integral to find the area of a curved shape, you are actually calculating the limit of a convergent sequence behind the scenes. Without this rigorous epsilon definition, we would have no logical foundation for physics, engineering, or computer algorithms that rely on approximations. To wrap up our lecture, let us reinforce the most important ideas we have covered today. First, a convergent sequence is simply an ordered list of numbers that eventually settles down around a specific target value. Second, we prove this convergence by showing that the distance between the sequence and the target can be made smaller than any imaginable error tolerance, epsilon. Finally, by finding a threshold index n where the sequence enters the safe zone and never leaves, we turn the abstract concept of getting closer into a rock-solid mathematical guarantee. You have now covered the full foundational topic of convergent sequences, giving you the absolute confidence needed to tackle the rest of calculus.